Welcome everyone back to the class. I understand a lot of you were accepted off the wait list yesterday, I believe. So welcome. The content from Tuesday's lecture, it's not necessarily that pertinent to the other things we'll be doing in the class, but I think it's interesting. I think you should take a look at it. It's all on the course website. I have a couple more announcements. So everyone who's here today will be who makes up the class, and you will be sent a permission code by tomorrow morning. I mean, I'd send it tonight. I'm going to a Warriors game though, so it'll be tomorrow. And if you didn't know, the deadline to add units without a fee is tomorrow, actually, at 11:59. I believe after tomorrow you can still add until the drop deadline, which is February 13th, I believe, but you might have to pay a $5 or $10 fee. So if you want to avoid the fee, just take the permission code and enroll tomorrow before midnight. Okay, so again, how it'll work is there's a unique CCN for our course that will apply to everybody. And then there's also student-specific enrollment codes that each one of you will get personalized. Okay, and so you can't share that code with anybody else. And yeah, so that will be unique to everyone. And so I understand a lot of students in this class are also in EE16A. And there's a time conflict, right? Because 16A lectures are also 3:30 to 5, Tuesday, Thursday. So I've emailed the CS enrollment people, and they've told me that it should work out that there are no conflicts. So like if you try and enroll in this class and you're already enrolled in 16A, things should work out properly. But in the event that they don't, just email me or the DeCal email with your student ID and the permission code that you were sent, and I'll forward it to the enrollment people so that they can enroll you manually into this class. Is that okay? That should work if you have any other time conflicts as well, if it's not E16A. Sounds good? Okay, and as well, along with your permission code, you should get an invite to Piazza, which is the forum we'll be using, and Gradescope, which is where you will submit homework. Okay? Homework 1 will be out late Friday or early Saturday, and it will be due next Friday, so February 8th at 11:59 p.m. on Gradescope as well. There's a question that you'll see in the attendance form today where I'm experimenting with potentially doing half of the homework be vitamin-style questions, as you might have seen in CS61B. So there would be multiple choice or select all that apply type questions for some of it, just to sort of make sure you're caught up with the basics and the terminology from lecture, and then some written questions. But if an overwhelming majority of the class doesn't really want that, then we probably won't do that. Okay, so feel free to express your opinions in the attendance form. Office hours will start next week, so we have one on Monday, one on Wednesday, and one on Thursday. They're all on the website. I believe it's 3 to 4 Monday, 7 to 8 Wednesday, and 2 to 3 Thursday, so right before lecture. And again, as I mentioned, content from last week's lecture, or not last week, Tuesday's lecture is available on the website. The slides I can usually post within an hour or two of lecture, along with any other supplemental materials. The video will usually take a little bit longer, so within a day hopefully, but probably not immediately right after. But it's okay because attendance is mandatory anyways. And based off of the votes from last class, the first quiz is going to be on Thursday, February 14th. So for those of you who weren't here last class, we're still on the wait list, there is the option of voting between Tuesday, February 12th and Thursday, February 14th for the first quiz. All of the other quiz dates are already on the website, and those are not going to change. The one we decided to go with was Thursday, February 14th. Okay? One thing to note is that this is one day after the drop deadline, but the quiz, it's not going to be too intense, so I don't think it would be a reason to drop the class either way. Yeah?
So it's during class time.
Yeah, all 5 quizzes are during class time. For the first, I'm not entirely sure if there will be 20 minutes or 30 minutes, but within the first half hour, so 3:40 to 4:10-ish. So try on the quiz dates, and we're still a while away from the first quiz, 2 weeks, I believe. Please try and get here as soon as possible on the quiz days. Okay, but we'll talk more about that once we get to it. Any questions, logistics-wise? No? Okay. So let's get into some of the core content for the course. Okay, so we're going to see a lot of notation today in the slides, and I'll explain it to the best of my ability as we see it. But here's just some of the pieces of notation that you'll see, just so that you're aware of it. Okay, so this upside down A symbol means for all. So one thing we'll often say is, for all x and x, for all y and y, for all students in this class, that sort of thing. The backwards E means there exists. Okay? And we'll see better examples of this terminology again later in the slides. This is just so that you're aware of it. There are three different pieces of notation that we use to mean such that. One is the colon. One is this vertical bar, this vertical divider. And another is S dot T dot. And it doesn't really matter which ones we use. Just in some contexts we use one, some contexts we use the other. And it's the sort of thing that you'll pick up as we go on. And lastly, this double right arrow means implies. Okay, and we'll talk a lot more about what this implication symbol means in a few lectures. But for now, all we really need to know is that this means implies. And that'll be good enough for today. So any question about all of this? And chapter 1.5 of the textbook for this class has a nice cheat sheet on a lot of the notation you'll see in the class. So if you ever forget, or are confused or want some more examples, navigate over to there, and you'll see a lot of examples of all this notation. Any questions with any of that? Okay, let's get into it. So first, we're going to define formally what a set is, and then talk about various types of set operations. Okay? So let's get into it. In mathematics, a set is just a well-defined collection of objects. Okay? And these objects need not necessarily be mathematic in nature. So oftentimes we'll be talking about, sets of numbers. You might have talked about, sets of vectors in another class. But there's nothing stopping us from talking about, for example, the set of students in this course. Right? These are all examples of sets. And what do we mean by well-defined? Well, by well-defined, we mean we can easily tell whether some sort of object is in the set or not. Right? So, for example, the group of students in this class, can we tell whether or not they're in this class? Yeah, it's pretty easy. I can just check B courses or whatever. Right? Can I check to see if... okay, actually, before we get into any more examples, a little bit more notation. So, oftentimes when we define a set, we use these curly brackets, right? Okay, and inside we write all of the members of the set, if it's a finite set, or we use dots to imply that there's some sort of pattern that's going on, right? So for example, a very, very common set, we'll see the integers 0, 1, 2, 3, 4, dot, 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 and then the reverse direction, -1, -2, -3, dot, 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 dot. Okay? So here it's implied that this set is not finite, right? Because we have the dots on either ends, and you can sort of fill in the pattern. It's a set of integers, right? And oftentimes we use the variable s for a set, but it really could be anything. And then here's a piece of notation. How do we denote that some object is in the set? Well, we say x is in S. So this means element of or is in. Okay, and that's this lowercase e looking creature. Is that okay? So for example, we could say this is actually the set of the integers, which we denote with this fancy z. Don't worry too much about that right now, because we'll talk a lot more about these different number sets and the properties that define them on Tuesday. But for example, we could say -3 is an element of z, right? But what we can also say is that pi is not an element of z. Okay, so the little e with the slash through it means is not an element of. Is that okay? So sets are made up of elements or members, and they're well defined, so we can tell if any member or any object is in the set or not. Yeah? Good question. So in sets, we usually care only about unique items. Okay? Good question. So in a set, and we're about to talk about the cardinality of a set, which talks about the number of elements in a set. We only care about unique elements. Good question. So as I mentioned before, there are two ways. There's the first way we can define the elements of a set, right? We can list them out, right? So for example, here we have A1 is just this finite collection of numbers. There's no dots anywhere. A2 is the same set we saw before, the set of integers. And A3 is the set of some basketball players. Okay, so as I mentioned before, it need not necessarily be mathematical in the way you're used to. But there's also another way we can define a set. okay, using what's called set builder notation. So with set builder notation, we sort of specify a rule that generates the elements of a set. So here for A4, what I'm saying is I want all elements X such that, remember this colon from the other slide means such that, I want all elements X such that X plus 3 is prime. Okay, so I go through, find all these X plus 3 elements, and then for those, I select the X's when X plus 3 is prime. Another way I could do this is say, give me all T's such that T squared minus 5T plus 6 is equal to 0. Okay? And again, the colon means such that. So for those of you who have taken 61A, what does this set builder notation remind you of? Yeah. An array, but there's something more specific, a type of paradigm. You know what I'm referring to. Someone said it. List comprehension, right? This looks very similar to list comprehension. So for example, I could have the set, let's just call it B, is the set of all elements that look like X squared such that X is between 0 and 10 and X is an integer. Is that okay? So this looks a little different. Before we were just specifying, X and T. Now here I'm specifying X squared, but that's okay. I just have to provide some description of what the element looks like and some condition. Is that okay? So this is saying all X squared such that X is an integer between 0 and 10, and that's inclusive. Okay, so that's one way I could describe this set. But in terms of list comprehension, this would just look like X, X star squared for X in range 11. Right? We want to take X going from 0 through 10 inclusive and square them, that gets our set. And this is how we do it in list comprehension. Is that okay? Any questions with set builder notation? Or any of the terminology you've used so far? Yeah?
When you say is prime, so is that allowed? Can you just explain that?
Yeah.
Okay.
Yeah. By the nature of a set, there's nothing stopping you from using words in English. And I mean, most of the examples you'll see in this class and in the future, you probably won't use words like that, but there's nothing invalid about what I just did. Yeah.
Is there like a limit to how many conditions you
No.
can have, or it's just like as many commas?
As descriptive as you need to be to describe the set. Yeah. Any other questions? Cool. So now an idea that we need to introduce, and this will be very crucial going into next week, is the cardinality of a set. And it sounds like a fancy word, but don't worry too much about it for now. The cardinality of a finite set S is the number of elements in it. Okay? And all we're talking about right now is for a finite set. Next week, we'll talk about infinite sets. Okay? And how we can measure the size of that. Right? Because right off the bat, in an infinite set, you can't just count the number of numbers in it, right? Because there's infinitely many. Right? So let's just do an example just to do it. Suppose A is 0, 1, 2, 3, 4, 5. What's the cardinality of A? 6, right? Because there's 6 elements in it. Just so that we have the example down, what if we had B is, -1, -1, 2, 2, 3, 4. What's the cardinality of B? It's not 6, it's 4, right? Because we only care about unique elements. Sets only consist of unique elements. Okay? So here, the cardinality is 4. And the elements themselves are -1, 2, 3, and 4. Okay? And just to get the thought stirring in your mind, we have the set of integers, dot, 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 -3, -2, -1, 0, 1, 2, dot, 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 dot. That's a terrible Z. Okay. What's the cardinality of the set of integers? We'll talk about it next week. Don't worry about it. Yeah.
It's not for B, we've got like duplicates, right? For example, we get another set C.
Yeah.
And we say -1, 2, 3, 4.
Yeah.
Can we say that B equals to C?
Well, it's really that B is not this. B actually is the set with just -1, 2, 3, 4.
So we can.
So you can. But so you'll never really see an example, I guess, out in the wild where there are duplicate elements in a set, because that's just not allowed. Is that okay? Cool. So now let's introduce this idea of subsets. Okay, so given some set A, we say another set B is a subset of A, if and only if, meaning the condition goes both ways, and we'll talk more about this next week. Every element in B is also an element in A. Okay, so if we want to draw some pictures, if this outer ring represents the set A, this inner set can represent the set B. Every element in B is also in A. Is that clear? Okay, so let's introduce some notation. So to say that B is a subset of A, you can say B subset A. It looks almost like a less than or equal to sign and a greater than or equal to sign. You know, in whatever year they teach it, they say the alligator points to the bigger thing. In this case, the bigger thing is the set with more elements. Okay, the same principle applies. Is that okay? So, just to give an example, let's say B is LeBron, Kobe, Jordan, and A is just LeBron and Kobe. We could say, in this case, A is a subset of B. Actually, just to keep the variables consistent in the example, why don't we say this is A and this is B, and here we could say B is a subset of A. Is that okay? So now there's another variant to this, right? So before, we had less than or equal to signs and less than signs. Right? What was the difference? In this one, equality is allowed, right? So we also have a similar notion for sets and subsets. So if I write this symbol without the bar underneath, we call this a proper subset. Okay, so this is read, B is a proper subset of A. And what does that mean? B is subset of A, and it's not the case that B and A are the same. Is that clear? Just like the fact that 3 is less than or equal to 4 means, 3 is less than 4, is the same condition as saying 3 is less than or equal to 4, and 3 is not equal to 4. So a proper subset is just a subset that's not equal. Is that okay? Proper subset is a set that's not equal. Okay? So actually, in the example that I've given, we could also say B is a proper subset of A, because A and B are not the same set. So it turns out we can also actually say every set is a subset of itself, right? Just like every number is less than or equal to itself, or greater than or equal to itself. Okay? Another quick variant on this, just before we move on, is that we can write the subset symbol the opposite way and say that it's a superset. Okay? So the equivalent notation for the ones that I've just written would be to write A is a superset of B, and A is a proper superset of B. And that looks a little too much like a less than or equal to sign. And these are the superset ones. And these are the subset. Is that okay? We're really just reversing. Yeah. And if you ever have any issues with remembering, like, what direction does it go, blah, 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 just think of less than or greater than signs. Is all of this okay? Okay, cool. So now let's start looking at set operations, okay? So the first one we'll talk about is the union of two sets. So we say the union of two sets, A and B, is a set of everything contained by either A or B, okay? So the best way to describe this is to draw a picture. You say this is set A, this is set B, and the union of the two is simply the set of everything that's contained by either one. Okay? And to write this both notationally and in set builder notation, the symbol is AUB almost. So that's what it looks like, AUB. And we can say that an element is in the union of A and B if X is in A or X is in B. Is that okay? So if X is in A or it's in B, we say it's in the union A or B. Notice, in this case, it's allowed to be in both, right? For example, all of the elements here are in both A and B, but it's still included in the union. The OR you might be thinking of is exclusive OR. Like for example, you go to Subway and you get a combo and they say you can get chips or a cookie. You don't get to have both chips and a cookie. It's chips or a cookie, but not both. And that type of OR is called an exclusive OR. Okay? We don't need to worry too much about that right now today. We're going to talk more in depth about, OR and exclusive OR and that sort of thing when we start talking about logic next week. But it's just to give you a preview of what's to come. Okay? Another way I could write this. X is in A or X is in B. So this V is another symbol that means OR. Okay? And it's actually called a disjunction. And we'll talk a lot more about it next week. But just wanted to introduce the notation. So X is in A or X is in B. Any questions with the union? Cool. So the next natural one to talk about is the intersection of two sets A and B. So let's go back to our picture. So if one circle represents set A, one represents set B, everything that's contained by both A and B is the union, or is the intersection, sorry. And the symbol for this is A upside down U, B. Is that okay? And let's define this with set builder notation. The intersection of A and B is a set of all elements X, such that X is in A and X is in B. Okay? And previously, we saw this disjunction, this V that opens up, just like the union symbol opens up. There's an equivalent for the end. It's the conjunction. That means that means and. Okay? So the last line says the same thing. The intersection of A and B is the set of all elements X, such that X is in A and X is in B. Okay? There's a special case when I have two sets that look a little like this. If this is set A and this is set B, what do we know about their intersections? It's nothing, right? And in this case, we call these two sets disjoint. So when the intersection of two sets has no elements in it, it's called disjoint. What does this symbol over here mean? It means the empty set, i.e. the set with no elements. Okay? And you can also write that as just open curly bracket, close curly bracket, the 0 with the line through it. I think it's a little more descriptive. Also, another thing to note is that the empty set is a subset of all other sets. Is that clear? It's a little more abstract, but it is true. And when we start, talking about how many possible subsets are there, and we're still weeks away from that, but that'll be a question we address. And that will come up once again. But just to get your mind on that. Yeah.
Is that derived from the proof we'll be doing, or any that's proven?
Yeah, we'll definitely talk about that. Okay. So is everyone okay with the notion of disjoint and just what in the intersection is? Cool. Okay. So now we have enough information to answer this question. Suppose A and B are two sets, and the cardinality of the intersection is a known quantity. Okay, notice how I read that. Cardinality of the intersection. Okay, we want to get used to talking about these symbols as if they're, regular English. How can we determine the cardinality of their union? Okay, so we know the cardinality of the intersection. How can we determine the cardinality of their union? I'll give you a minute or so to talk amongst your peers, and then we'll take it up. So discuss. Cardinalities of A and B, yeah. Are what? You can assume that for now. For sure. Okay, let's come back together. Okay, so how do we know, or how can we determine the cardinality of the union of A and B? Any ideas? Yeah.
A, like the union minus the intersection. I guess A plus B minus the intersection.
Okay, and how did you get that?
Because when you add A and B, you're counting the intersection twice.
Exactly. So let's visualize this. Okay? So if we wanted to count the number of elements in the union of A and B, well, a good way to start would just be adding the number of elements in A and the number of elements in B. So why don't we do that? Okay, so first we'll add the number of elements in A. So why don't we say A union B is the number of elements in A plus, change the color, number of elements in B, right? And then what do you notice? Well, we counted this overlap region, i.e. the intersection, was double counted. But we only want every element in this Venn diagram to be counted once. Is that clear? So what do we do to account for the fact that it was double counted? We can subtract it. Is that clear? And so this principle is called the principle of inclusion-exclusion. Okay. And we can actually extend it to 3 sets or 4 sets or an arbitrarily many, or arbitrarily large many sets. Okay? And actually one of the questions that will be in your homework this week, one will be to reprove this, but another question will be, can you derive the principle of inclusion and exclusion for 3 sets? And you'll do a similar thing. You'll add up the individual cardinalities, cardinality of A plus cardinality of B plus cardinality of C, and then you'll have to look at what was double counted. But there will actually be another step. Okay? But I'll save that for the whole. Yeah.
Is there like a formula for n number of sets?
Yeah. And so there is, and it's actually one of the questions on your homework this week. It's actually one of the optional ones, but we can talk more about it in class after the homework is due. Okay? So is this general idea okay? Principle of inclusion-exclusion. This will be very important. We'll come back to it and do more actual questions where we can count things when we get to the counting part of the course. But for right now, all we care about is deriving these sort of things. Everything okay? Cool. So now here's another set operation. We say the difference of 2 sets A and B is the set of everything contained in A but not contained in B. Okay, so I'm not good at drawing circles, but okay, here. A and B. The difference is the set of everything in A but not in B. So what would that look like? That's set difference. There's some different notation that we can use for it. One is just simply A minus B. Another is this A backslash B. Oftentimes we use the latter one because it doesn't look like a minus sign, right? And I mean, sets are not numbers. You can't add and subtract them. The only operations you can do on sets are the ones we're talking about. You know, you can take the union of 2 sets, the intersection, find the cardinality, the difference, blah, blah, blah. But there's no operation that's like A plus B. That's not a thing, unless you define it. Okay? So, well, either of these are both, perfectly valid, but just to avoid confusion, we oftentimes go with the latter. In terms of set builder notation, what this looks like is X is in A, and X is not in B. So again, this reads, the difference between A and B is the set of everything that's in A and not in B. Okay? And notice, the difference of B and A is something completely different, right? The difference between B and A is the set of everything that's in B and not in A. Is that okay? Cool. And then, not that you'll necessarily have to do this, but another way to count the number of elements in the union of a set would be to add up the number of elements in A minus B, plus the number of elements in B minus A, plus the number of elements in the intersection. Because notice, there's no overlap between any of those quantities. Is that okay? Just something to think about. Okay, so the last operation we'll talk about is this thing called the Cartesian product. Okay? And when you hear Cartesian, the thing you probably think of is, the Cartesian plane, which is, real number line on the x-axis, real number line on the y-axis. And you'll see why with the way a Cartesian product is defined. So the Cartesian product of 2 sets is the set of all possible combinations of one element in A and one element in B. Okay? So the symbol we use is just the regular multiplication symbol. And the way we define it is the set of all ordered pairs, x comma y, and I'll use this bar just to introduce more notation, such that x is in A and y is in B. That's what we call the Cartesian product. So for example, why don't we say A is 1, 2, 3, and B is x, y, z. Okay? Let's look at the Cartesian product of A and B. So it's every possible combination of taking the first element being in A, and the second element in being B. So we could have 1 comma x, 1 comma y, 1 comma z, 2 comma x, all the way till 2 comma z, all the way until 3 comma z. Okay? And I could have enumerated this in a different way. So what I did was first I combined 1 with all of the elements in B, and then 2 with all of the elements in B, and then 3 with all of the elements in B. I could have done it the other way around. I could have done 1x, 2x, and 3x, and then 1y all the way until 3z. And that's okay, because sets inherently aren't ordered. Usually when we look at the integers, there's a natural way to order them. It just makes sense like that. But if we're looking at any finite set, there's no order to it. Just like I don't know if they talk about sets in 61A, but in 61B, if you've seen that, the set object has no order. Unlike a list where this is the 0th element, this is the first element, so on and so forth, the set object is completely unordered. Okay? What we can't say, though, is that this is the same as the set of ordered pairs x comma 1, y comma 1, z comma 1. That's something else. That's the Cartesian product of B and A. That's different, right? So we want to look at that. The Cartesian product of B and A would look something like this set. x1, y1, z1, all the way until z3. That's a different set. Because so the items that are in the set are ordered pairs. And while sets don't really care about order, ordered pairs, well, they're ordered, right? So the order matters within the ordered pair. It matters that this is the coordinate that comes from set B, and this is the coordinate that comes from set A. Is that okay? So the Cartesian product of A and B is not the Cartesian product of B and A, as we just saw. Yeah, you had a question?
Is it possible for us to not have all the different combinations and just restrict ourselves to the first element of A with the first element of B and so on and so forth?
So you're talking about a subset of the Cartesian product.
Yeah.
That's something we're about to talk about in 1 or 2 slides. Okay, let me just see if... Okay, no. There's another question I wanted to ask. So before, we looked at the cardinality of the union of 2 sets. Right? What's the cardinality of the Cartesian product of 2 sets? So this is a bad example because they both have the same number of elements. But you can sort of generalize the pattern. I guess I can just ask it. What is this quantity? Good. It's the product of the individual cardinalities. And can you see why? Because for every element in X, we map it to every single element in Y. So for example, if we're looking at the possible second coordinates when A is equal to 1, there's 3 of them. And then when A is equal to 2, there's 3 of them. And then when A is equal to 3, there's 3 of them. So what ends up happening is we multiply the individual cardinalities. Is that okay? So the cardinality of the Cartesian product is just the product of the individual cardinalities. Okay, and lastly, to see where this idea of the Cartesian plane comes from, or when we talk about vectors, oftentimes you'll see this notation that looks like r squared, right? Well, what that really means is just the Cartesian product of the set of real numbers with the set of real numbers, okay? Which is why, when you think of any point on the Cartesian plane, it's just a set of ordered pairs where the first element is a real number and the second element is a real number. Yeah?
If you have multiple, more than 2 sets, does that move the cardinality still apply?
Yep.
Okay.
Yep. You can actually take a Cartesian product of as many sets as you want. And so, for example, if you take in Math 54, or I guess E16A or B, you'll often see something that looks like r to the n, which represents n length vectors. Well, all that really is you can just represent each vector as n points, where each coordinate comes from the set of real numbers. Is that okay? Yeah.
If there's an element that's in both A and B, then doesn't the rule about cardinality apply?
No, because we still only bundle one element in A and one element in B. So it's okay if we had, like for example, if X was 1 instead. We would just have an ordered pair, 1, 1. Is that okay? Cool, so that's a good question. Any other questions about set operations so far? Okay, I'll keep moving forward because we have a lot of things to cover today. We have 40 slides. I don't know if we're going to get through it all. Okay, so another thing we need to discuss when we're talking about sets is this idea of a universe. That's usually denoted with this fancy U. And you'll see a lot of characters that have this fancy lettering. I tried to draw a Z with a additional line, or R with this additional line. I guess mathematicians just like to be fancy, but I mean it is how it is. A universe usually just represents the set of all objects under consideration. Okay? So for example, if we're looking at different subsets of undergrads at Berkeley, our universe could be the set of all undergraduates at Berkeley. All undergraduates, right? And then every subset you create will be a subset of the universe. Okay? And so this allows us to talk about this notion of a complement, which is everything that's in a universe, but not in our set. So let's look at an example. Suppose our universe is a set 1, 2, 3, all the way until 20. Actually, excuse me, let's just make it 10 so I don't have to write as much. And we say A is 2, 4, 6, 8. The complement of A will be the set of all elements that are in the universe, but that are not in A. Is that clear? So that would look like, 1, 3, 5, 7, 9, 10. So it's the set of everything that's in the universe, but not in A. Right? And the notation we use for this, usually AC, complement of A. So for example, what would be the complement of the set of students in this class? Well, it would be the set of all the students at Berkeley that are not in this class. If our universe is the set of all students at Berkeley. If our universe was the set of all people on Earth, then the complement of the set of students in this class would be everyone on Earth that's not in this class. Is that okay? Yeah.
Can you write A like that?
Yeah, another way you might have seen it is A prime, or even sometimes in probability you might have seen A bar. They're all equivalent. Different books use different things. Yeah.
What's the difference between a complement and the difference?
Well, so the difference doesn't really need a universe to be defined. So if we go back to, for example, the set difference here, we could have A be 1, 2, 3, 4, and B be 3, 4, and we get that the difference between A and B is just 1 and 2, but there is no universe defined here. The complement is essentially the difference with the universe. Is that okay? So another way to look at a complement is the universe, the set difference between the universe and our set. And just to be thorough, if we want to put this in set builder notation, it's a set of all elements that are in the universe and not in A. Yes, in the back.
It's like B is a subset of A.
Yeah.
And if you're trying to complement B, is it still just have to do with the universe?
Yeah. Complement, you always look at the universe. Yeah. So any questions with this? A lot of notation we could use. The one we'll probably use a lot in this class is the exponent C one. Not exponent, but you get what I mean. We might just throw in the other ones just so you're familiar with that. Any questions about all of this? Cool. De Morgan's laws, I think I'll save this to be a homework question or something that you can play around with in homework. But essentially, De Morgan's laws allow us to convert between the complement of a union to the intersection of two complements. And we can convert between the complement of an intersection to the union of two complements. Is that okay? So we won't do any formal proofs or anything like that right now. But I guess we could do an example. Why don't we let our universe be 1, 2, 3, all the way till 10. We can let A be 1, 2, 3, 5, 6, 10. And B can be 2, 4, 6, 8, 10. So why don't we evaluate the first one? Okay. What's the union of A and B? Well, we take every element that's either in A or in B, right? So 1 is in both, or 1 is in at least one of them. 2 is in at least one of them. 3 is in at least one of them. 4 is in at least one of them. 5 is, 6 is, 8 is, and 10 is. Is that clear? Okay, so what's the complement of A union B? 7 and 9, good. Now let's look at A's complement and B's complement individually. Well, what's A's complement? We probably want a 4. We have 5, 6, so we probably want 7, 8, 9. So 4, 7, 8, 9. And what's B's complement? Well, we want all the odd numbers, right? So 1 through 9. 1, 3, 5, 7, 9. We intersect A and B, A's complement and B's complement. What are the only elements that are shared between the two? 7 and 9, right? And we see that these two things happen to be equal. Is that clear? And so something I want to emphasize, this is not a proof. Might even box that. Okay, that's not a proof. All we did was just come up with one example and show that it happens to be true. Right? Maybe there's something mysterious, like magical about the numbers 1 to 10 that made this work. Okay, we don't know for sure. And so to be rigorous, what we would have to do is show that regardless of what elements are in A and what elements are in B, and the situation is with their overlap, that this always holds to be true. And that's something we will do at some point. It may be a question that you walk through on the homework. It might be something we do next class, but we will see. And I'll tell you right now, the homework will appear to be long in terms of the amount of text that you have to read, but the amount of work that you have to do individually is relatively short. And I mean, if you've taken E16A or 16B or whatever, it's a similar style. There's a lot of reading to teach you a new concept, but the amount of work that you actually have to do is relatively minimal. Okay, so if there is a quote-unquote proof of this in the homework, it will walk you through it. Okay, and we haven't formally talked about this word proof and what it exactly means, so we won't go too in-depth with this until we start covering what a proof actually is, but it's just something to look out for. So any questions with De Morgan's laws? Okay, cool. So now let's start talking about what a function is. Cool. So, before we talk about a function, we have to talk about what a relation is. Okay? So a relation with domain A and codomain B is a subset of the Cartesian product of A and B. So you've probably heard of functions and relations before. My guess is they probably weren't defined this way. But let's look at an example. Okay? So why don't we let A be the set 1, 2, 3, 4, and B be the set 1, 5, 7. The Cartesian product, I'm not going to list it out, but I can just say it looks like 1, 1, 2, 1, ... all the way until 4, 5, 4, 7. a relation is just any subset of these ordered pairs. Right? Because the Cartesian product is the set of all possible combinations, one element in A and one element in B. So that's the Cartesian product. And so some relation can be any subset of this. Okay, so for example, why don't we say R is, 1, 1, 1, 7, 3, 5, 4, 1, 4, 5. Do you agree that R is a relation with domain A and codomain B? Would you agree with that statement? Is R a relation with domain A and codomain B? Yeah, it is. Because every ordered pair that we see in R, right, for now, R is just a set, right? You might be thinking ahead and thinking of functions and f of x, this and that. I didn't write that down on the page at all. All I'm saying is that R, this relation, is a subset of the Cartesian product of A and B. Yeah.
What's a codomain?
The codomain is the set that makes up the second coordinate in an ordered pair. For now, that's all we've talked about in terms of domains and codomains. Okay? So for now, all we care about is that we're looking at the Cartesian product of A and B and taking some subset of that. We're calling the first coordinate in each of these the domain and the second coordinate the codomain. Is that okay? So to write it explicitly, R is a relation with domain A and codomain B. Okay? And what does a relation mean? It just tells you that these input and output pairs, which is one way you can think of it, are related in some way. So all this is telling us is that 1 and 1 are somehow related, 1 and 7 are also somehow related, 3 and 5 are related, 4 and 1 are related, and 4 and 5 are related. Okay? And the relation is just this set R. Okay? So relation is a set. Any questions with this? It's a pretty abstract definition, but it will translate nicely into when we define what a function is. Any questions with this? Does this sort of answer your question about taking a subset of the Cartesian product? Okay? So now you're thinking about functions. Okay? What is a function? Well, so a function is a type of relation. Okay? So a function with domain A and codomain B is a subset of the Cartesian product of A and B, such that for every element in A, there's exactly one element in B. So with this definition, a function is also just some subset of the Cartesian product, but one that satisfies the rule that for every element in A, there's exactly one element in B. Not 0 elements in B, not 2 elements in B, exactly one element in B. Okay? So why don't we copy this over, just to do the example. No, not that. Okay. Paste, maybe. Nice. Okay. Cool. So why don't we write a potential function with this domain and codomain? Okay? So what we know is that for every element in A, we pick exactly one element in B. So all this means is that a function is a relation that looks something like 1 comma something, 2 comma something, 3 comma something, and 4 comma something. Because what we're saying is that for every single element in A, there has to be exactly one output. So you can think of A as your set of inputs, and B as your set of outputs. And you can think of this as just being the condition that for every input, there's exactly one output. Is that okay? So a potential function that we could create is, I don't know, 1, 1, 2, 1, 3, 5, 4, 1. That's a function. It doesn't matter that the output elements are repeated. All that we care about is that for every potential input, every element in A, we map it, that's a new word, map, to exactly one element in B. And that is how we define a function. Each A and A is mapped to exactly one B and B. And this is something you may be familiar with already. And you've probably heard of the horizontal line test. Does that sort of sound familiar? Right. And you sort of go across the page, and if at any point your function, if at any point the vertical line intersects 2 points, you know it's not a function. All that means is that for some input, so for some x value, you have multiple outputs. And that's identical to this condition. So I guess I can write it down. Horizontal line test. Oh, sorry, yeah. You get what I mean. Vertical line test. Sorry about that. Okay. Sorry about that mistake. I meant the vertical line test. You sort of take the ruler, go across the page, make sure it doesn't intersect 2 points at the same time. Vertical line test. Is that okay? Yeah.
Is this like saying it's a 1, 2?
No. So that's a different type of function, and we'll talk about that in just a bit. So any questions with the definition of a function? Okay. So again, all we've said so far is that a function is just some subset of the Cartesian product of two sets. And most of the time our functions will be between numbers and numbers, but we haven't restricted that in any way. So for example, we could say A is a set of strings hi and hey, and B is the set of numbers 5 and 10. The Cartesian product of A and B would be the set of ordered pairs hi 5, hi 10, hey 5, and hey 10. So here's a question. Are the following relations, they're all relations, I guess we can write that. Are they functions? Is f a function? Yes or no? Yes. Right? Because there's some output for hi and there's some output for hey. Is g a function? Yes. Because for hi there's some output and for hey there's some output. Is h a function? No. Because there's 2 outputs for hi and there's only supposed to be 1. And there's 0 outputs for hey and there's supposed to be 1. So 2 outputs for hi, 0 outputs for hey. So they're all relations, but only f and g are functions. Cool. So, as I mentioned before, the domain is the set of all possible inputs. It's that first coordinate in the ordered pair. The codomain is the set of all possible outputs. It's the set of what could make up that second coordinate. And one way we can sort of represent this is f, a, right arrow, b, or the function maps elements in A to elements in B. The second one we probably won't write too much, but it's there. And notice, when I'm writing f at A is equal to B, I'm talking about the set A and the set B, not an individual element. Right, so that's set A and set B. Okay? So now we raise the question, what's the difference between a codomain and a range? Right? The codomain is the set of all possible outputs. But notice, when we go back to the function g, right, the set of all possible outputs was 5 and 10, because that's what b was. But what were the actual outputs for g? Just 5, right? So in that case, the set of all actual outputs is just the set 5 of the number 5. And the set of the set of actual outputs is the set of just 5. And the set of possible outputs is the set 5 and 10, right? So that's the difference between codomain and range. The range is the set of all actual outputs. So why don't we write this out explicitly? For f, what's the codomain? Well, we're assuming that we're still using a and b, so it's just b, which is 5 and 10. But for f, what is the range? What is the set of all actual outputs in f? We're looking at f here. 5 and 10, it's the same thing. Is that clear? What about G? The codomain is the same. Still 5, 10. What about the range for G? It's just the set 5. Okay? So the codomain is the set of all possible outputs, while the range is the set of all actual outputs that are actually seen. Yeah?
You said that like every element in A has to have the exact one element in B.
Yeah.
But is it possible for functions to have like discontinuities?
That's sort of outside of the scope of the definition of what we're talking about right now. That's more of like a calculus type of question, if that makes sense. Yeah.
Wait, how is the codomain 5 and 10 for G?
Because, sorry, I guess this segment at the top should also be repeated there. But we said that B is 5 and 10. And we're saying F and G are both subsets of A cross B. Is that okay? Another nice picture that people like to draw when defining functions, and this will be useful when we start talking about other types of functions, is this dot diagram. Okay? Where the left side represents the domain, right side represents the codomain. And the circles on the left represent elements in the domain, and the circles on the right represent elements in the codomain. And all we care about for a function is that for every circle in the domain, there's exactly one arrow coming out of it. So for example, multiple arrows can point to the same circle in the codomain. That's okay. Some elements in the codomain might not necessarily have an arrow pointing towards it, but all we care about in the definition of just a pure function is that every circle in the domain has one and exactly one arrow coming out of it. And in terms of sets and subsets, the codomain is always a subset of the range. It could be equal to the range. So for example, in F, the codomain and range are equal. But that won't necessarily be the case in every function we look at. And we'll study different functions with different combinations of these properties. You have a question? Sorry, yeah, it's the other way around. Good catch. The range is a subset of the codomain. Good clarification. Because the codomain is a set of all possible outputs, and the range is the set of all actual outputs. So the range might be equal to the codomain, but it might be smaller than it. Yeah?
It's not always true that F and G are proper subsets of the product of A and B, right? It's like if B is only one element.
Yeah, that's a good point. But if B has multiple elements, is it possible for it to be a non-proper subset? Or is it possible for them to be equal? No, because you have multiple outputs for each input.
So just in this example, that's true.
Pardon?
Just in this example, the top is true.
Well, in almost all functions you look at, it will be a proper subset. Cool. Yeah?
So this definition only applies if it's 2 dimensions, right? So if we have like x, y, if you have like 3 inputs.
Not necessarily, because we didn't specify what A and B had to be. A could be a set of ordered pairs itself, right? So if we're thinking of, if you've taken Math 53, you have multivariate functions, ones that look like, for example, f of x, y, is equal to, I don't know, e to the xy plus x squared or something. This is also a function that satisfies this definition. But it's one where we take ordered pairs and send them to real numbers. Okay, so all functions will be of this one. Okay? And this is another image that sort of describes the relationship between domain, codomain, and range. The red is the domain, codomain, and this is the range. So as you can see, the range will always be a subset of the codomain. Cool. And so in order to define a function, we specify the domain and codomain and how to map elements of the domain to the codomain. Right? So we can do this in two ways. We can list out the pairs as we've been doing, but that's, in the future, not necessarily what we'll do. Usually what we'll do is specify a rule that describes how to get from input to the corresponding output, right? And so there are two different notations that we can use. One is f of x is equal to x squared, and that's probably the one you'll see most of the time. But another is this f colon x and this arrow to x squared. And notice the difference between the right arrow and the right arrow with the flat tail. The one without the tail tells you the function maps from domain to codomain, but the one with the tail tells you the rule itself. Is that clear? So the one without the flat tail tells you f is just some function with this domain and this codomain. The one with the flat tail tells you f is some function that maps elements that look like this to elements that look like this. Is that clear? There's an important distinction between those two types of arrows. Okay? And functions need not necessarily be algebraic. So we could also have f of x is equal to the x, the smallest prime number. That's also a rule that specifies how to take us from input to output. Is that clear? Cool. So, okay, what I'll do is cover as much of the next content as I can in the next, let's say, 6 or so minutes, and I'll leave the last 5 minutes for you to complete attendance. And also there's a short, there's one question I have on the attendance on whether or not you'd like multiple choice questions on the homework. And also 2 quick quiz questions from things we just talked about in lecture, just to see how well you've retained the knowledge. Okay, they're not graded or anything. I just sort of want to see what people put on those. And try and answer them independently of the people near you. But I know that's difficult in such a tight setting. Yeah?
Will multiple choice questions be in addition to or like replacing?
In addition to. Yeah, no matter what, part of the homework will definitely be you writing out math because that's how math is done. The reason we would have some multiple choice questions is to test little things like if you know the definition of this term or that term. Okay? But no matter what, on each homework there will be several questions where you have to sit there and write out math because there isn't really another way to do math. Is that okay? Yeah.
Does CSAT do multiple choice?
No. But that doesn't mean necessarily that we're not going to do it, if that makes sense. Okay, let's get into what an injection is. Okay, so now we're going to look at, sorry, I guess I should have said this. We're going to look at a few different related types of functions. Okay? And each of these are types of functions, and there's some relationship between them, which I guess we'll get to next lecture. But that's something you should know. Okay? So, we say an injection between A and B. A function is an injection if no two elements in the input have the same output. Okay? And so I'll get to this weird mathematical looking thing in a second. But why don't we go back to this drawing with circles. So let's just say we have okay, so if this function is an injection, I need to make sure that no two arrows point to the same circle. Is that clear? Because we're saying that no two elements in the input have the same output. So no two arrows okay? So let's see. I can point this one to this one, this one to this one, this one to this one. Aha! Now I'm stuck. Is it possible for me to have an injection between these two sets? No. Right? Because what would I map the fourth element in the domain to? It's impossible. So, and that's a question that the conclusion to which you'll see, maybe in Wimby we'll get to it today. But now if this is our set, then sure, I can have an injection. Because now, no two arrows point to the same dot. This is a perfectly valid injection. Yeah?
But don't we have point something towards the last argument as well?
No. In the definition of a function, we never said that every output has to be hit. Right? That's why there's a distinction between codomain and range. Codomain is all possible outputs. The range is all actually hit outputs. Right? And so I guess just to reinforce it, we can say this is the range, while this entire thing is a codomain. Is that clear? Okay, and now let's try and decipher this Greek-looking thing. Okay, it says upside down A, X, Y, E, A, comma. Okay, what does it mean? So what this says is for all X and Y in the domain, if f of X is equal to f of Y, it must mean that X and Y are the same element. Okay? And all we're saying is that no two elements in the input have the same output. An equivalent way of writing this statement is for all X and Y in A, if X and Y aren't equal, that implies, and remember this means implies, f of X and f of Y are not equal. That might be a more straightforward way to look at it. For all elements in the domain, if they're not equal, their outputs won't be equal. And in the pictorial interpretation of that is that no two arrows will point to the same circle. So any questions with what an injection is? Sometimes we call injections one-to-one. Right? Does that sort of clarify things? But there's a difference between a one-to-one function and a one-to-one correspondence, which is a distinction I guess we will see next week. But we say a function is injective or an injection or one-to-one if no two elements in the input have the same input. Sound okay? And both of these are examples of injections. Is that clear? Okay? One quick thing I wanted to get to before we move on is an algebraic test we can use to see if a function is an injection. So we use the vertical line test to see if if a relation is a function, right? So vertical line test. So we can actually use something called the horizontal line test to see if it's an injection, right? And let me draw some examples of real functions. By real I mean on the Cartesian plane that are and are not injections. Okay, so is that function an injection? The one I just drew? Yes. Injection. But is that an injection? No, because it maps multiple inputs to the same output. So for example, it maps, if this was f of x equals x squared, my drawing's pretty bad, but it will map f of 1 will map 1 and negative 1 both to the same output. But last time I checked, 1 is not negative 1. Right? So this function is not an injection. So what we could do is check to see if our function is strictly increasing or strictly decreasing to see if it will ever output the same thing multiple times. Right? If I ignore the left half of this drawing and just look at the right part. Well, okay, my drawing's just bad, but just that part. Now we're just looking at the right tail. The function is only increasing. So if some point we have the point to the right of it and immediately to the right of that, will always be larger, it's impossible that our function will output the same thing multiple times. In order for a function to output the same thing multiple times, it must reach a local maximum or local minimum and then change directions. Is that clear? So what's one test in terms of derivatives we could use to see if a function is an injection or not? What we could do is take the derivative of a function and see if it's always greater than 0 or always less than 0. Right? If a function's derivative is always greater than 0, strictly increasing. And if it's always less than 0, we can say it's strictly decreasing. And if it's one of these two things, always increasing or always decreasing, it's never going to reach a local maximum or local minimum and change directions. So that means every output will be unique. Is that sort of clear? So we could use this derivative test. So for example, if we have h of x is x cubed plus 3x, I don't know how to draw that, but what I can do is take the derivative, 3x squared plus 3, and I know x squared is always greater than or equal to 0, so x squared plus 3 will always be strictly greater than 0. Is that clear? This is greater than or equal to 3, which is greater than 0, so this is strictly increasing. So that means this is an injection. Is that clear? Okay, that's where we'll leave it for today. Before you go, make sure you fill out this attendance, or you may risk getting dropped from the class. You'll get invites to Piazza and Gradescope tomorrow, along with your permission code. And if you have any conflicts with E16A, make sure to, first try, see if it works. But if it doesn't, just let me know and we'll take care of it. Okay?